Okay, maybe we should get started. So, I was going to go through this one, but Elin, you had a question with the homework. Do you want to talk about that first?
It's okay. Just a little typo.
Oh. Well, okay. Well, why don't you just point out which is the typo? Because
homework 9.
Homework 9.
So we give an example.
Okay. So, homework 9. Okay, so homework 9. Okay, yeah, this one.
And you give an example of chaining as to base A and base B.
Yep.
But if there's something is wrong, you should shift the order of the two,
So you're saying what this basis is wrong? May well be. Yeah.
This is right, but rewrite it in another places. I think there's something wrong.
So which question are you talking about?
It's not a question.
Oh, it's not a question.
For example.
My example?
Yeah.
Like, which equation are you talking about?
I think that you should substitute A0 to A1.
A0 to A1.
And then A1 to A0.
Doing the phi in the expression of the...
Yeah.
So are you talking about this one, this equation?
Yeah.
Right. Okay. So you're saying that maybe that transformation might have an error in it?
Yeah.
Okay. Well, let's check that. So A0, A1 is just 0, 1. So okay. And then B0, B1. So we need to rewrite this thing in terms of, so we've got B0 is cosine, sine pi over 8. 0. May well be an error. Wouldn't be entirely surprised. Cosine pi over 8, 0 plus sine pi over 8. Okay, so we need to invert this formula to give 0 state. So we multiply the top one by sine pi over 8 and bottom one by cosine pi over 8, and then add them, then this will be 1. Meanwhile, yeah, okay, so let's just do that properly. So sine pi over 8 B0 plus cosine pi over 8 B1 is going to be equal to, it's going to be like a sine squared cos squared term. Sorry, I won't bother writing the angle there. And then plus minus sine pi over 8 cos pi over 8. And we're adding it. So this one is sine pi over 8 cos pi over 8. So this one cancels out. So, and this is 1. So basically 0 is equal to that. And so I think similarly we can, so it's going to be cosine pi over 8 B0 minus plus sine pi pi over 8 B1 is going to be the one state. And it's supposed to be substituting this into the state, what is it? 1, 0, 1, 0, this is Alice, this is Bob. To that state. Alright, so so we just have to make our transformations. A1 is 1, and then and then the 0 on Bob's side, so we use this formula. So it's sine pi over 8 B0 plus cosine pi over 8 B1. Okay, so is that already a typo there? Yeah, okay. Yeah, it's probably just it that the A0 and 1 are. Yeah, I think the A0 and the 1 are in the wrong spots, is that right? And then the one state is minus cosine pi over 8 B0 plus sine pi over 8 B1 minus cosine sine. Yeah, right. So it's just the A0 and the A1 that are in the wrong.
Yeah.
Yep. Okay.
Okay. It's not a big matter.
Yep. Okay. Okay. Okay, so then let's recap what we were doing last lecture. So it's a little while, so let me sort of do a bit of summary. So what we're going to now talk about is how the wave function can also evolve in time. We haven't really been talking about anything happening in time up until this point. We've just been sort of describing the state as a sort of a static kind of quantum wave function vector, but actually, you know, in practice, it often evolves in time. So how does it evolve in time? Firstly, how do we write something that's evolving in time? It's very simple, just these coefficients of the wave function change with time. There's basically an equation that tells you how things evolve with time, and this is Schrodinger's equation, and the normal way that it's written is like here, where it's in this sort of differential form, where you've got the time derivative of the vector is equal to some Hamiltonian times state. We'll explain, I'll be explaining all these things as we proceed in this lecture. But actually the way that I'll be dealing with in this lecture is really more this exponential form. These are completely equivalent ways of writing the same equation. So if you have an initial state at some initial time, psi 0, and then the rule or the sort of law of nature, if you like, of how it evolves in time is given by this exponential minus it Hamiltonian over h bar, and that gives you the new state. And so let's try and firstly understand what this equation actually means. So t is time, that's how much time you're going to evolve forwards. H bar is some constant, and the Hamiltonian, and this is really where all the kind of, this is the whole difficult part of this whole thing actually. So the Hamiltonian is something that tells you what states have what energies. Right? So this could be sort of, it depends upon the physical situation what the Hamiltonian is. Just like, in a classical physics problem, there's all kinds of different situations that you can think of with a ball being kicked in the air. The ball could the landscape is different or something like this. Gravity could be different. So there's all kinds of different physical situations. And that is basically all encapsulated in this Hamiltonian. The way the Hamiltonian is pretty simple. It's basically it's a matrix which has a particular set of energy states. So there are some particular states that have a particular energy. So in this atomic case, then these might be the energy levels of an atom, and these are sort of distinct orthogonal states, and they have a particular energy, right? So that's just how separated these states are. And as usual, these energy states are orthogonal and normalized. So I think this is more or less where we got up to last time. So I started giving you a couple of examples of what kind of Hamiltonians this could be for qubits. So this is more or less real life examples. I've got something like an atom in mind. Well, not something like an atom. Really, I've got an atom in mind. Okay. So these are energy levels of an atom, and well, you guys are not physics students, but in physics you learn that if you put an atom in a magnetic field, then the energy levels actually move up and down. And so if you put a magnet in this atom, then these energy levels will, one might go up, one might go down. And the way that you might describe that is, so B is like the strength of the magnetic field. I might write a Hamiltonian that looks something like this, where, say this state 0, say it goes down when you apply the magnetic field. Say this one goes up, right? So that's why this has got a minus sign, that's got a plus sign. Yeah. So in this situation, the Hamiltonian that you would write is just something like this, and so the amount that it would go up or down is proportional to this size of the magnetic field. So the stronger the magnetic field, the more it goes up and down. So if you take the magnet away, then these energy levels might be the same energy. So we write it just like this, or if you like a matrix notation, then it'll look like that. And we've dealt with these matrices like x, y, z, which keep on coming up. So in this case, the Hamiltonian is some constant, this b multiplied by this z Pauli matrix. But it doesn't always have to be in this diagonal form, and this is because just like how we were learning with how you can have different bases to describe different states. So remember, if you're doing a measurement, this is not really anything to do with measurement, but remember when we were talking about measurement, you could be measuring in the 0, 1 basis or plus minus basis or some other basis. Just like that, the Hamiltonian could also be in some other basis which is not 0, 1, right? So it could be in some funny basis where the individual states are not just like straight 0 or 1, but some superposition. So this plus and minus is some superposition state. And remember, plus is the state of it's 1 over root 2, 0 plus 1, and then minus is the same state, but with a minus sign. So that's also possible, and I won't really go into reasons why, but if you shine a laser on an atom, this is the kind of Hamiltonian that you get. So the laser kind of, well, you might intuitively kind of think the laser sort of prefers the atoms to be in this kind of state. If you might sort of like So what that means is that if the atom was originally here, shine a laser then, it would be more like here. So if this atom was originally in the zero state, the laser shines on it and creates a kind of a transition between the 0 and 1. We'll see more about that shortly. But right now, all I want you to sort of understand here is that the Hamiltonian could be, is made like this. It's basically some energies multiplied by a bunch of states in this outer product form. Basically makes this matrix, and the states don't necessarily need to be just 0 or 1. It could be actually anything. That just depends upon the physical situation. So there you have to ask some physicists to tell you what's the Hamiltonian. Basically, the Hamiltonian often is like the central thing of the physical problem. So, in any kind of physics paper that's talking about quantum physics, usually there's some Hamiltonian somewhere in the paper towards the beginning, and then that in principle tells you everything about the system. It might be difficult to solve, but it's kind of the core essence of some physical process. Okay, so now let's talk a little bit about the maths of how you actually work this out, right? So I've told you that, okay, so this is somehow the rule, Schrodinger's equation, of how you work out what the state is going to be sometime later, right? Okay, so I've told you the formula, but how on earth do you actually work out what that is? Because if you think about it, what you've got here is a little bit of a tricky thing here, because it's not just like some exponential, which would just be a number, but actually it's exponential of some matrix, right? So that's a little bit of a, that's a sort of a bit of a nasty kind of object. It's not surprising that you get something a little bit nasty, because the original form of the original form of the Schrodinger equation was some differential equation. Right? So, there's no shortcuts. Basically, you have to, even if you write it like this, you've got some nasty thing that you've got to deal with. Or you could solve the differential equation. Either one, basically. Either way gets you the same answer. So, what does it mean to exponentiate a matrix? I don't know. Do you guys do this kind of thing in maths much?
Yes, in linear algebra.
Ah, you already do it in linear. Okay, good. So if you're familiar with it, then that's great. But just to recap, the meaning of exponentiating a matrix is that if you remember, the Taylor series for exponential is just some series like this. So the meaning of exponentiating a matrix is basically that it's exactly the Taylor series, except that now you've got a matrix and you sum all that stuff there. So of course it's in general a little bit messy to calculate, because even the meaning of this thing, or to work out what that matrix actually is, you've got some infinite series to sum, right? And if you've got an I in there, then nothing really changes so much. It's just got an I floating around. So if it's m squared with an I there, that one becomes a minus sign. This one becomes minus I, so forth. Okay, but exponential of a matrix is, in general, this kind of nasty sum that you've got to work out. But in general, it's actually kind of hard to calculate. So even if I told you the Hamiltonian, and I said, okay, work out what the state is going to do 5 seconds later, if the Hamiltonian is super complicated, it's actually quite a difficult problem. But in some cases, it's not so hard. And fortunately for qubits, it's relatively easy. You can handle it pretty easily. So now let's talk a little bit about how you actually do this for a qubit. Actually, for this first case, for this case where the Hamiltonian was proportional to this Z matrix, and remember this Z matrix is this diagonal matrix, right? It's 1 minus 1 on the diagonal. So actually, if it's a diagonal matrix, actually it's always easy. So even if the matrix was really big, it's always easy because you guys are math students, so you know, go a little bit.
Of diagonal matrix is just the power of the elements on the diagonal.
Yes, that's right. Yes. So for a diagonal matrix, exactly. So you got some general Hamiltonian, and you got energy 0, energy 1, energy 2, so forth, and all these are 0. Then, so if you want to do e to the I h t over h bar, then because this is I h t over h bar, so this would be minus h squared t squared h bar dot dot dot. And as Danny just said there, taking the power of a diagonal matrix is easy because you can easily work out that all these are, you know, when you multiply these rows and columns, they don't really interfere with each other. So h to the power of n is just simply these things to the power of n. So working out this, a diagonal matrix is always easy. And so in that case, basically what you're going to have is this identity matrix will be just 1, 1, 1, 1, 1 like this. This one will be, okay, let's just pull out this factor of e to the IHT. So E0, E1, dot, dot, dot. Next term will be IT of h bar squared, squared, dot, dot, dot. So, so actually, you know, each of these diagonals, you can sum them all up because these are just individually just the exponentials, right? So you can work out that this one will be e to, oh, I forgot a minus sign. Okay, anyway. Oops, 1. So basically, along the diagonal, it's just the exponentials of, you know, e to the I of the energy t of h bar of each of these energies that you have here. So it's always, so you can always do that. So that's basically what I've got here. I did a slightly different way. Next slide, I will explain what I'm talking about here. Okay, so for this one, you can just follow this explanation. All right, so then this e to the minus IHT, so I've got the minus sign there, sorry about that, but that's going to be this matrix. Now we've worked out the matrix, the hard part is done. Then to work out what the state is sometime later, all you need to do is just multiply this matrix by the initial state. Okay, so say the initial state was this thing, alpha beta, just a general state. And then all I have to do to work out what the state is sometime later is simply just multiply this state by this matrix, simple matrix multiplication, and you get this. So what you see is actually what this thing does is actually to multiply this alpha beta by some phases. Right. And so I'll give you an example of how to sort of visualize this state, which is kind of famous example. So let me just take the example of, say, the initial state is 1 over root 2, 1, 1. Okay. I've written alpha, beta, but I'm just going to choose this initial state. So if you remember, if I draw this state on the block sphere, that was the z direction. This was x. This is y. Do you guys remember which direction or where that state is on the block sphere?
Wait, isn't block sphere supposed to be like 0 pointing up and like 1 pointing down?
Yeah, that's right. Yeah. I don't mean that this is here. I mean that's the state that I'm going to start with. And so you're right that the top of the block sphere is the state 1, 0, and the bottom is 0, 1.
So what's the meaning of the x, y? Is it just like a 3-dimensional space?
So remember, the reason why we have the block sphere is because if you remember, let's say I have an arbitrary state that's like this: cosine theta over 2 plus I e to the I phi of sine theta over 2, right? So here's my, okay, I'll call it something else. Here's my state phi, okay? And then if you work out what the average values, expectation values of the x operator is, then this will be cosine phi sine phi, sorry, cosine theta sine phi. Sine. Got it wrong. Sine theta cosine phi. Y was sine theta sine phi, and Z was cosine phi. Okay. And this is a general state for a qubit. And so the reason why we parameterize it like this is so that when we look at expectation values, these are exactly like coordinates for spherical angles. Yeah? So that for a general state, you know, in the usual spherical coordinate way, you know, the angle with respect to the z-axis is phi, and then the angle with the x direction is phi, right? Yeah. So just you know, just to match it up with what you're saying before. So the reason why at the top of the sphere 1, 0 is at the top, it's because, so 1, 0 means that the state is just this one, right? So that means if it's only this one, then we need theta to be 0, and, well, it doesn't really matter what that is actually. And so if theta is 0, then it's at the North Pole. Yeah? For the state 1, we need sine theta over 2 to be 1, and that happens when theta is pi. So that's at the South Pole. So this is just a parameterization to visualize all the possible states. Okay. So basically, I'm just asking you. So if I had this state 1, 1, do you guys remember where that state is on the block sphere?
So it should be pi over 2, so it should be on the xy plane.
Yep.
And around the circle, the bigger circle.
But what about phi? So okay, so you correctly said that theta should be pi over 2, so that's correct.
Phi should be 0.
Right, phi should be 0, yeah. And phi is this angle with respect to x. Yeah. In other words, that state there is this located right here. So it's pointing in the x direction because theta is pi over 2 and phi is 0 for this particular state. Okay, so now, so that I prepare my state like that, and then now I apply a magnetic field, and then Schrodinger's equation is telling us that the state sometime t later is going to be that. Okay. So let's look at the example that we're doing here. So alpha and beta are both 1 over root 2. And so this is going to be I beta t over h bar minus I b, something like this. Okay. And we can pull out, just to make this sort of a little bit more obvious, I can pull out this factor of I bt over h bar as a global phase. Well, and then I can make it even more obvious for you by writing it in bracket notation. This is 2I bt over h bar. Okay. So after I evolve the Schrodinger equation, it's going to turn into this state. Okay, and then, it's got this B, T, and H bar and all these things, but basically all these things are just numbers, right? So B is just some magnetic field apply, H bar is also some number, T is just some time. Then, can you sort of see what is going to happen to this? Or how do, sometime T later, where is this state going to evolve to? On the block sphere. Okay, let me give you a hint. Let me just call all these variables B, T, over H bar. Let me just call that X. Too physicsy for you guys. No?
Is it just a coefficient or a matrix? The exponential?
Okay, maybe I shouldn't have called it x. This x is nothing to do with this x. It's just some number that, is just that bunch of numbers. It's just something, some magnetic field, some time, h bar we know. But as time goes, maybe I should call it tau. This is what I actually normally do when I write a paper or something like that. I usually call this thing tau, which is something like time, but just like, rescaled. So depending on tau, which is like the time, up to some various funny numbers, the state will change like this. Yeah. So if I were to track how this state is changing over time and view it on the Bloch sphere, what do you think it would be doing, or where would the state go to after some time on the Bloch sphere?
Like it's rotating around the circle.
Yeah. So which circle?
The XY plane.
Yes, XY plane. Exactly. Yes. So exactly. Yeah. So this is just some phase here, right? And remember, the general form is also some phase here on this one. We had this global phase here, but actually that doesn't really matter. It's basically just this relative phase between the coefficient of the 0 and the coefficient of the 1. And so actually, if we had 2t or minus 2t equals to phi, then that would be that, right? So basically what's happening here is that this thing will be, if you watch this in time, you're basically going around the equator. The angle would be according to this. So when tau is, pi over 2 or something, it would be on the other side, right? Because it's times by 2. And it would just go around and around on the equator of this Bloch sphere. So basically, this is what Schrodinger's equation does. It sort of, what we're talking about up until this point is that, we're just talking about states, and the states were not moving or anything like that. Now you can, literally see some movement, right? So, we've visualized it on the Bloch sphere, but the state is now changing as a function of time, and it's changing in this way. Right? Okay. Okay, so that was a relatively simple example. Okay, but now we also had this other example where the Hamiltonian was the states of the Hamiltonian were not just like 0 or 1, but some other states. So in this example, the actual energy states are like the plus minus states. Yeah. Okay, so this is where we need to use a little bit of some mathematical tricks to actually evaluate the matrix exponential, because now the Hamiltonian is not just a diagonal matrix, it's actually some off-diagonal, well, x is, what x is? X is the x operator, which is the same as this x, by the way. The x operator is some off-diagonal operator. And, if it's off-diagonal, doing all these matrix powers, it's not going to be something like, that to the power of n or something. It's simply not. So we need to work out some way of handling it. Now, okay, so in the general case, it's a little bit tricky. But for the qubit case, it's actually not so hard. Well, it's not so hard if you know how to do it. Okay, so alright, so let me fix up this minus sign here to start with. So sorry, this one was minus, this one is like that. Okay. Let me do another power here. So h cubed is going to be plus I h cubed t cubed over h cubed. Now, oh, sorry, I've forgotten the factorials. Silly me. 2 and 6, yeah. Sorry about that. There's a couple of factorials that we're missing. Okay, so I think that's now correct. Okay, so now in our case, let's substitute h is equal to x. Okay, let me omit the factors of omega for now. In fact, just so that everything looks. Okay. Okay, so imagine if H is just our matrix X. Okay, as I said, this X matrix, the powers of a non-diagonal matrix are in general complicated, but there's one simple fact that you can use that actually simplifies this a lot. So firstly, let's just work out what x squared is. And if you do that, so that one is 1, this column is 0, this column is 0, this one is 1. And actually, x squared is actually identity matrix. So that's quite good, because we can actually get a general formula for any power, because basically if you had like x to the power of 5, obviously that's x squared, x, right? So, and then I've said that these are identity, so actually x5 is just x. So basically x to the power of n is equal to x if n is odd, and I if n is even. So that actually makes our life pretty simple, because when we substitute this x into here, well, we've got even and odd powers, and for all the even ones, it's just going to be I, and all the odd ones, it's going to be x. So we can use that relation to simplify this. So here's the I, h bar. So let's collect all the even terms. So it's going to be, well, I times by 1. So that, so this is even. Next even term is this one. So this is t squared over 2h bar squared. Dot 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 dot. Now let's look at the odd terms, and we know all of them are going to be just x. So this is going to be I t over h bar. Next one is I t cubed over h bar cubed 6. And that's it, right? Oh well, okay, obviously dot 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 for all the odd powers. And then all you have to do is just notice that, oh, actually that's just cosine, right? So this is going to be I times n, just regular cosine, not just, no matrices, just the regular functional cosine. T h bar. So if I had put this omega factor, this cosine would have also had an omega here, but didn't do that. And over here, all these things also have a factor of I, and it's just like a single I. So let me just pull that out. Ix, and this one is going to be sine. Wait a minute. I'm missing a minus sign. Oh yeah, okay. Because that's got a minus sign. It's got a minus sign there. Yeah. Alright, so then that's got a minus sign. So when you pull out a minus I, then this will be minus t cubed and so forth. Yeah, I think the sign, the next term, as a different sign, yeah. So I think that's correct. So sine t of h. So, and we can write that in matrix form because, you know, this thing, this I is just like 1, 1 diagonal. This x is 0 like this. So we can actually write it exactly as a 2 by 2 matrix. And we've managed to do the matrix exponentiation. So, you know, I sort of emphasize that this is a sort of a special case. We would not have been able to do that if there was no simple rule like this. Right? So if it wasn't the case that x just had this even odd simple rule, we'd have to go and either sum this whole series or do something complicated like that. Okay, so now that we've worked out what the actual matrix is, life is simple. We've got the matrix, multiply it by, say, the initial state. This time I'm going to choose the initial state that's 1, 0. And if I multiply that, then I get something like this. And you can see that for different times, well, okay, so we can draw this on the block sphere too. Different color. Okay, so this time my initial state is here, right? And so let's think of, so if omega t over h bar, let's call that x this time. Then our general state after some time is going to be cosine x minus I sine x. So in this case, can you see which or where it's going to move on the block sphere? Yep, YZ plane, yeah, that's right. And so you can see that because, so firstly it's cosine sine, right? So it already looks exactly like this one. So we can already make an association that x is theta over 2. And then this minus I thing must be to this e to the I phi, right? So e to the I minus I, e to the I phi is equal to minus I. So phi must be what? Yep, minus pi over 2. So basically what happens is that as time, okay, maybe I should call it tau or something again, but as time goes forward, it starts up here, and then at, well, when x is pi over 4 here, then it's in this minus pi over 2 direction. So in other words, it will go around sort of like that. It will go around the ZY plane, and just go around and around. see here that, well, just alluding from the example, I didn't really tell you any physics of why this happens. But, okay, so if you shoot a laser, then you can go around the Bloch sphere like this way, right? If you apply a magnetic field, it goes around this way. You know? So, of course, if you do both of those things, then actually you can get to any point on the Bloch sphere, because combine those two things, you know, you could go down a bit, rotate a bit, you know, go down a bit more, then you can reach any point in the Bloch sphere. Okay, any questions? At this point, I think, you know, there might be sort of a few kind of new things that are coming up which make you feel like you don't understand everything. But, you know, so there are some parts which I don't really expect you to really understand, like, you know, why does the laser give that Hamiltonian, you know? Okay, that part I just told you that it is, so no need to worry about that really. You can kind of leave that to the physicists to tell you why that is. So I think at this point, the level of understanding that I'm kind of looking for is that, well, okay, so firstly, Schrodinger equation, you know, it's such an equation, it tells you how it evolves forward in time. You know, there's this thing called a Hamiltonian that kind of tells you it's something about the physical system, and that totally depends upon what kind of operations or what kind of environment this atom is in, right? So in a way, that's a sort of a given, right? So somebody has to tell you what that is. And then there's the mathematical aspect, which is, okay, well, all right, so I know the Hamiltonian, somebody's told me what that is. I know what the Schrodinger equation is because that's the same all the time. Okay, so how do I calculate it? Well, yeah, so the calculation aspect is done, at least for these cases, like this. So I think if you understand those points, then that's enough.
Professor, I have a question.
Yep.
So if the angle phi is pi over 2, then should it rotate in the opposite direction?
Yeah, that's right. So if it were that somehow that if it were that there was no minus sign here, I think that's sort of what you're asking. Yes, it would be rotating in the opposite direction. And you can see that actually two ways. Firstly, just by looking at this and going, okay, well, now it's I, it's not minus I. In other words, the phi angle is the opposite, right? Or you can notice the fact that sine is an odd function, and this minus sign, you can absorb it into the inside the sign, and then there's a you know, the time is minus time. In other words, everything's running backwards. So that's another way you can actually see it.
So we're constructing our coordinates according to the right-hand rule. So if we set all the coordinates in another rule, will it change?
No, I think if you wanted to go in the opposite direction, then, you know, the Hamiltonian will have to change. So, you know, that might happen if this was minus omega x. And the using right-hand coordinate system, I think we have to always stick to that because, well, that's more or less our definition of our visualization. So, of course, you're free to do any visualization, like you can start to plot all your graphs so that it's like, you know, everything's upside down, but it'll just confuse everybody. So, I think when you draw the Bloch sphere, you have to stick to the usual coordinate convention. Okay, all right. So, just to finish off this set of slides. So I think a lot of this I've already said, but basically, this form of the Schrodinger equation is, you have your initial state, which is a vector. Then this junk here, exponential Hamiltonian, that's some kind of matrix, right? And of course, so if you apply a matrix to a vector, then you get a new vector. But this matrix has some kind of special properties. It's not just any old matrix. It is a so-called, it's always a unitary matrix. One thing maybe I forgot to mention is that the Hamiltonian is actually always a Hermitian matrix, because actually it's also an observable. So the Hamiltonian is quite a important object in terms of Schrodinger's equation. But if you remember when we were doing that chapter on observables, this is exactly the same form of an observable that we had, right? If you remember that chapter with the boxes and the particles, right? So I said okay, so if it's in this box, it's this state, and then we're going to assign some values to each of those states, right? So I can just assign whatever values I like, -1, 5, or something. This takes exactly the same form. So it's a bunch of states which happen to be the energy states of some system, and then it's whatever those energies are. So even though this is kind of a very special matrix that has a big role in terms of Schrodinger's equation, but actually it's also observable, so it totally makes sense to say, what is the expectation value of the Hamiltonian? In fact, what that would give is basically the average energy. So it's the average energy. So if you did that, then you'd be finding the average energy. I think even in the midterm, I gave you a question that was like that, where I said, okay, this state has this energy, that state has that energy, what's the average energy? I didn't call it Hamiltonian because I thought it would confuse you. Normally in physics you call that energy observable, the Hamiltonian. So anyway, so all observables are actually Hermitian. Did I say that? I can't remember if I said that in the chapter, but yeah, all observables are always Hermitian, and Hermitian means, so if you have an observable doing the Hermitian conjugate gives the same. And the reason why all observables need to be Hermitian is because that guarantees that any averages are always going to give real values. So we don't want observables to give complex values. And if you have an exponential of a Hermitian matrix, then it gives a so-called unitary matrix. Did you guys do unitary matrices in linear algebra?
Couldn't remember probably.
Yeah, okay. Yeah, okay. So there's this so-called, another class of matrices called the unitary matrix. And the unitary matrix has this particular property, which is that the inverse of the matrix is just given by the Hermitian conjugate. I think when I first saw this in quantum mechanics class, all these different matrix classes, I was trying to avoid doing any maths in my physics course, so I didn't properly appreciate all these things. But actually, this is a really kind of a pretty weird fact, because as you know, finding the inverse of a matrix is usually a pretty hard kind of task, right? And it's usually, you can't just do it so easily. But taking the Hermitian conjugate is really super easy. You just transpose, change do a complex conjugate, and then it's already the inverse of the actual matrix, right? So it's actually kind of a pretty remarkable sort of property, right? And so the significance of this is that basically what unitary operations always do is that they're always like some kind of basis rotation, actually. So for example, maybe a better way to say it is that applying a unitary matrix, there's always some kind of rotation in this space, right, along some kind of axes. And how do you know it's a rotation? Well, for example, let's say you apply some unitary operation on some state. Okay, so you can keep it totally abstract like this. Now, we know that the original state is a normalized state, right? Now let's check that the rotated state, whether it's normalized or not. So take the inner product with itself. By definition, it's that, right? But a unitary matrix, U dagger, is equal to U inverse. That's what a unitary matrix is. And then U inverse U, this cancels, and then you just get just the initial states, and that's 1. So a unitary rotation never changes the length of the vector. It's you can of course have some matrices that change the length, but unitary rotations always leave the length of the vector the same. So basically the only type of operation that you can have in that case is that it's this type of rotation. And you can also show that you can always reverse the operation of the Schrodinger equation simply by applying the kind of the operator with the plus sign. Right? So remember the matrix that we apply in the Schrodinger equation, this has got a minus sign. But if we just apply the same thing with a plus sign, then because this is actually just the conjugate transpose of the original U matrix, then this cancels and you get the same state. So, okay. Okay, so maybe just to finish up, let's just do this question maybe. Okay. So, actually, I think we did already something very similar to this, so maybe we don't really have to do it in a lot of detail. So, just if you have this situation where the Hamiltonian is this X type Hamiltonian, and I'm just giving you some real numbers here, but basically the way that you do it is pretty much exactly like how I explained on the board here. I had a slightly different initial state for this question, but the matrix as we derived just before is equal to that. That's the Schrodinger time evolution matrix. Just apply it to that state, okay, and just get some stuff like this. And then you can just plug in these numbers into this formula, and then you'll get some new vector. Kind of a bit of a random example, but yeah. But very similar to what I did there already. this is the last slide for this set. Okay, so we've got only 5 minutes left, so maybe, so there's one kind of choice that we can make here. So originally what I had planned, I was going to talk a little bit about the Schrodinger equation as it's done kind of normally in the wave function form. So Schrodinger equation, normally how you taught it is, well, I want to just quickly show you the slides, see if you like it. So this is how actually, so any physics student, if you ever take a quantum mechanics course, probably quite early on, you're shown this equation, and you're taught to solve this. Now this looks a little bit different to what we've been doing, but because this is actually how it's normally taught, I thought it might be a good thing that even though actually we don't really need any of the content in this slide set at all, but just for the fact that, well, you're doing a whole quantum mechanics introduction course, and if you never saw the Schrodinger equation in its normal form, then maybe I thought that would be kind of a weird thing. So we could go through this, or if you want to just get onto quantum gates and stuff like that as quickly as possible, we could skip this. We could come back to it later, of course, if there's time. What would you prefer?
I think since our assignment is closely related to quantum gates, we can get to quantum gates first and then
Okay.
Refer to
Yeah.
the like more quantum mechanics side
Yeah.
of the issue.
Maybe we can come back to this. Okay.
Does that sound?
Yeah, I agree.
Okay. All right. Fine. Yeah. Okay. Well, I hope we can come back to it. Yeah. All right. Then maybe next lecture we will start on quantum gates and so forth. Something else. Okay. Well, we've got 5 minutes left, so why don't we just do like one slide? Okay. All right. So quantum gates, finally. All right. So, so quantum gates are based exactly on the thing that we were just talking about with the Schrodinger equation. So, the main equation that we're going to be using is exactly this Schrodinger equation form. So, so that's the basic sort of physics that we're going to be using, but kind of just more from a technological perspective. Since the early days of quantum mechanics, what people kind of considered when they were looking at the Schrodinger equation, so obviously, Mr. Schrodinger discovered the Schrodinger equation, and kind of what he had in mind then is that more or less that the Hamiltonian is just something that is given to us by nature, right? So it's we're just going to describe a physical system, and apparently it behaves in this way. So basically, for almost I don't know, maybe like 80 years, 50 to 80 years or so, people kind of more or less considering that this Hamiltonian is just something that's sort of given to us by nature. But just more recently, people have been able to devise more and more complex experimental systems, so that increasingly, actually, this Hamiltonian, which was supposed to be, well, initially just something which is, describing physical quantum states. So, the classical kind of problem that you look at in quantum mechanics is like describing the states of an atom. So you consider the hydrogen atom, and then you say, oh, the energy levels of a hydrogen atom are this and this and this, and we can calculate it, and then we can go to the lab, and then we look at a hydrogen atom and say, oh, it matches exactly, great. It's sort of, it's gone from sort of that situation to saying, well, actually, we can, if we shoot this laser and then apply this field and do all this, then we can make this Hamiltonian, and then we can control our state in the way that we would like. Right? So we're gradually moving on from being sort of passive observers of quantum systems to sort of active participants, where we can actually control quantum systems and make them do what we want. So basically, that this is really what a quantum computer is. Actually, it's wouldn't say just, but it's basically an extremely controllable quantum system where we can control the Hamiltonian and decide how the quantum state is going to move. And by doing that, we can execute quantum algorithms and so forth. And basically what quantum gates are really just an example of that. So, okay, so I think that's probably all we have time for this week. So we'll continue on with that next week.